Yes, sir.
Yes, sir. It's me.
Okay, so this example in yesterday, all the candidate keys. So just to recall that first you have to draw vertices corresponding to attributes in R and then draw directed edges depending upon the FDs given. For example, A arrow BC, so you have two arrows, two edges emanating from A, vertex A to B and C and so on. And then collect all the groups VNI and VOI we have already seen, and whatever the attributes you have in VNI, no incoming, forms the candidate key. But in order to verify whether it is correct, we need to find whether it includes all the attributes of R, for which we need to find the attribute closure. So AG is the set of attributes we have in VNI. So find the attribute closure. So it includes all the attributes, all 6. Hence, this is the only candidate key. So that completes the problem. So we will take some more examples. Right, so we have here again 6 attributes and these are the FDs given, right? So first FD is A arrow B, so we just draw an edge from A to B, right? Yeah, if any doubt is there, you can raise. So it's very simple. AB arrow E. So both A and B, you should start writing edges towards E. So both A and B, you can see that it ends with E because E is the dependent side, AB on the determinant side. That's why dependent side cannot be formed as a key. That's the reason why we don't take into account. But some attributes may appear on either side. For example, C is appearing on left as well as right. So there is an ambiguity whether it can form determinant or dependent. Okay. Now, if it appears only on left, that means no incoming edges. That's a perfect candidate key. That's part of it. Okay. So A arrow B, AB arrow E. Next one is BH arrow C. So both from B and H, we need to write edge towards C. You can see that H it goes here, B also goes to C. So C on the receiving side. C arrow D. So straightforward you can write C arrow D. Now D arrow A. So this again goes because A now you can see both left as well as right. So there is an edge written. So now this completes the dependency graph. Now we have to write VNI and VOI. That means attributes, attributes or vertices were only incoming. So which are those attributes? We have to find VNI. In other words, it should appear only on the left hand side. It should not appear on the right side. Which are those attributes? Yeah, anybody can answer.
H, sir.
Yeah, H there is only outgoing. There is nothing which comes into it. That means it's not appearing on the right. You can see here in the FD also H is appearing on only left. H is not appearing on the right. So no incoming. Okay, you can start from A itself. There is an incoming. B there is an incoming. C there is an incoming. D, there is an incoming. E, incoming. H, there is no incoming. So H is correct. Now all the, okay, not all. What are the other which appear only on the right hand side? That means receiving side. Sorry. See, again start from A. A, outgoing as well as incoming. So that's not the one which you are looking for. Only incoming. That means B, incoming as well as outgoing. C, incoming as well as outgoing. D, incoming as well as outgoing. E is only incoming. That means you can see here E appears only on the right hand side. E is not appearing on the left. So that cannot be taken for the this one. Candidate key. See, any attribute which appears only on right is not part of the candidate key. 100%. Attribute which appears only on the left, that is no incoming, is 100% candidate key. But when I say 100%, there is a but. Unless and until you find its attribute closure. So H, we have already said that it is part of the candidate key. Now we will calculate the attribute closure of H. So we'll start from H, and for each FD, see whether that left hand side attribute is a subset of this. A is not a subset, AB is not a subset, BH is not a subset, C is not a subset, D is not a subset. So the attribute closure of H, that is H plus, is H only. So it's not including, right, all the attributes of R. Hence, this cannot be a candidate key. It is not able to determine all the rest. It is something like, you know, USN is given and is unable to find even name. It's unable to find its address. I mean, his or her address. Then what is the use? It cannot be called as a key. So that's the idea. Now what to do? So when, see, we say that H appears only on the left, but we don't conclude that this can be a candidate key. So what to do? Now we have to pick the attributes where the ambiguity is there. Like in this case, see, I have I have A which appears on either side, that is both incoming and outgoing. B also same, C also same, D also same. See, E you cannot, because it perfectly appears on the right, so this cannot be a candidate key. But A, B, C, D, since it appears on either side, that is both incoming and outgoing, I can just borrow one attribute at a time from this set along with H, because I need to help H in order to make sure whether I can get a candidate key. So what I'll do one thing, I'll just take A first because H has to be there. So I'll try to see whether this gives me a candidate key. That means find its attribute closure. So start with AH, right? Start with AH. Now go through the attribute closure algorithm. That is, take each FD, see whether left hand side is a subset. If so, include B. So take left, that is A, is a subset of this, hence include B. The next FD is AB. So the AB is a subset of AHB. So include E. Right? Next BH. BH is also a subset of this. So you can include C. Then C is a subset, so D you can include. So we have 6 attributes, all 6 have come. Hence AH has to be a candidate key. Next what you do, you borrow B also. and see whether that fellow also can find. So H is mandatory. I'm just adding B. So BH plus you can find. So start with BH. Start with BH. Now A, it's not there as a subset. Next AB is not a subset. BH is a subset. OK, so now we have C could be included. C is a subset of this. So D I can include and A I can include. Now since A has come, A is a subset. The outer for loop will get executed. So B also B of there. E all changes. You should keep on trying this FDs. So I have all 6 attributes. Now BH also is a candidate key. Now similarly take C and also D individually. Don't take A, B, B, it should be a minimal set. So we should start with a single attribute at any time. So AH, BH, CH, DH. I've shown you AH and BH. You can try for CH and DH, see whether it includes all the attributes, and if so, then it has to be the candidate key. So this is the method. You can see that even CH and DH will include all the attributes, and so we have 4 candidate keys now for this relation AH, BH, CH and DH. You can see that H is part of each and every key because H appears only on the left hand side. So it has to be a determinant. Whereas A, B, C, D, since it's appearing on both the sides, we are not sure whether it could be called as a candidate key or not. So we need to try it out. I mean, find its attribute closure. So it's very easy to ascertain. Now, any doubts?
No, sir.
So you will get a problem 100%. You have to work out, number of problems so that it's easy, because this is going to be the key step in normalization process. OK, without this, you can't do normalization. So now we can, instead of even, putting it all together, what I have shown you the steps earlier in the algorithmic form, because this is my own algorithm, putting all these concepts together, because you don't get these things in the book, Navate or Ramakrishnan, nowhere. This is out of my research and research papers, and Navate gives one exhaustive algorithm, but I'll tell you that. But otherwise, this will be a very easy method for finding the candidate key. Right, so you can find this in my book as well. Now what I do is this time, in order to store these attributes which appear only on the left, only on the right, both sides, by drawing the dependency graph, all that, because you can get this data, but you need some variables to store this information, the attributes, like, we have VNI group, we need, to store these attributes. Again, VOI, we need to store these attributes. On either side also we need to store. So I call left hand side is one set, right hand side is another variable, set variable, both sides is another set variable, and candidate key. Ultimately, which are the attributes which form the candidate key. That's a set again. So all these are set variables. Initially, let us assume that all are empty. Okay. Then we can build the dependency graph and then start adding the attributes to these variables, set variables. So from the graph, you can compute what? All vertices with 0 in degree. That means no incoming edge. So that means only left hand side. They appear only on the left. With 0 out degree, which means right. See, these are all can be easily done. You have done, I think, in first semester or second semester some C programs on arrays and sorry, no, not that, ADA. Yeah, DAA subject you would have seen, you know. How do you represent a graph? What are the methods available to represent a graph? Varsha. Varsha is there. Varsha is there. Varsha. Varsha. This is the problem. They just log in and vanish. Varsha. Okay, I think I'm forced to put absent for Varsha. I'm sorry.
Yes, sir.
Now you have come. I'm
So
just
no, sir,
network problem. Oh, but it is not showing anything here. It's still, you know, enabled. Okay, tell me, what are the ways by which we can represent a graph? 2 ways you have already studied, correct? Yeah, you can unmute and keep it. What is there? Why do you want to simply mute it again? You have to speak something, no? Hello, Varsha.
Yes, sir.
Keep it unmuted. Don't mute it. Tell me. See, here it should be an interactive class, right? What is so problematic for unmuting? Sorry, muting. Huh? Yeah, tell me. You have studied about graph, right? Graphs.
Yes, sir.
Graph is set of vertices and edges. So how do we represent it in memory? You have studied that in last year, just last year, last semester, sorry. Correct? Two ways to represent your graph.
Matrix and adjacency.
What matrix? There is a name for that, right? Adjacency matrix, you have heard of?
Yes, sir.
Next, one more method.
Adjacency list.
Huh?
Adjacency list.
Adjacency list. Okay, so now you have this. What I'm talking about is adjacency matrix kind of thing, which you can use very easily in order to find this. I think you would have done some programming also using all this. Okay, you can mute it. So from the graph, we can just calculate adjacency graph in the sense using adjacency matrix or list. So get all the vertices with 0 in degree, that means which appears only on the left, and 0 out degree, which means only on the right. Attributes which appear on the both. So that's what we have seen in the problems. Okay, now step number 4 is peculiar. I'll show you an example for this. See, we had at least one attribute in the left hand side. Now supposing, assume that See, in this case, one attribute. Now assume that this is also not there. Attributes may appear only on the right or both the sides. See, this could be empty. So that's what it says. If left hand side and right hand side also empty, that means all the attributes appear both left as well as right. Then that means all attributes in both the sides set. Then it's a very exhaustive algorithm. Actually, the complexity of this is exponential. So that's what Navate gives you. So I'll give you an example for this later. So in such cases, we need to use algorithm of 3. Okay. What is that algorithm of 3? We will see that later. Okay. Else, that means assume that this is not the case. We may get some attributes in left hand side or right hand side or both. So in case if this is not true, which means we have some attributes in left hand side. So find its attribute closure and see whether it includes all the attributes in R, which means that that has to be the candidate key. Right? Then job is done. But supposing if it doesn't include all attributes, then you come to step 6. Then pick one attribute at a time that belongs to both the sides. That's what we did, no? See, H did not give the all the attributes from R. So what we did, we just picked one at a time from this both the sides. Okay. So pick one attribute A that belongs to both the sides and see whether that gives me. See, whatever you have found from left hand side and join that with this attribute and find its attribute closure. If it is equal to R, then that should be, you can see here, then there should be a candidate key added. Next, you can, get the next attribute. So this is a for loop. So this will do what? Every time you pick an attribute from A and join with the original both the sides. And because you have already included A, so just remove that from this. See H, for example, I would have started with from both the sides. I would have included A and found the attribute closure. Now this is equal to R and hence AH is a candidate key. Now you have to remove A. So that is this step, ls minus A. So you are left with H. Again pick one more from both the sides, say B, and again find the attribute closure, etc. etc. So this you could repeat and then keep adding this candidate key into CK group or set, and after that you can return CK. So whatever we have shown in the example, exactly the same, I just put it in the algorithm. Right. So any doubts in this algorithm? Right. So we have now only this one. Supposing if we have empty left hand side and empty right hand side, everything goes into both the sides, then what to do? So we have an example here. This is a typical example. You can see here A incoming, outgoing, B outgoing, incoming, you can see here, C same, D, E, everywhere, all attributes you will have both incoming and outgoing. That means my left hand side set is empty. My right hand side is also empty, right? And my both the sides, all attributes, everything, A, B, C, D, E, F. Now how to compute the, see, it's not so easy. So how to do it? Oh, I'm not given the solution. Yeah, now you can tell me. Okay, I'll give you a very simple example. Real world example. See, I have R with USN, comma, name. Right? USN, comma, name. And FD, one is USN arrow name, and FD2 name arrow USN. So what is my left hand side? Adwin. Adwin is there. Adwin not there. Okay, Fatima.
Yes, sir.
Tell me this group, which are the attributes? Quickly.
Sir, null.
Null, good. Next.
And even RS is null.
Good.
And both are USN and names.
Right. Okay, now what to do? Same logic. You pick something from here if it's there. If it's not there, null only. And pick one at a time from both the sides. So null union USN is
USN.
USN only. So find its attribute closure. Correct?
Yes,
so,
sir.
So first FD USN determine, I mean is a this one subset. Okay, start with USN. So USN is what? Is a subset
So
of
USN
this.
and
So
name, sir.
I can include name. Correct? So USN is a candidate key. Next you take name because I need one more attributes left out with the BS, that is both the sides. So calculate, you start with the name and second FD actually determines USN. So now my CK, now you can include both the attributes. So my CK list or set will be USN alone can find it. They are determined name also. So this is the second candidate key. That means USN and name both are candidate keys. So what does it mean? That name also is unique. That means a name can determine USN. Name has to be unique because I'm giving this FD, right? USN alone, not something like, okay, instead of name, you can take even phone number, right? Mobile number. Mobile number has to be unique for a person. So what we or email ID, anything you can take. So if we can find using USN all the rest of the attributes, it's fine. And using name, I can determine everywhere. I'm guaranteeing you that it is a unique one. And hence, even if I don't have here, my logic should be, exhaustive algorithm should be, pick one attribute at a time from this both the sides, right? And see whether it includes all. If it includes, fine, you get the candidate key. Now, in case if single attributes do not find, then you take two attributes at a time and then see whether it. If that also doesn't, go for 3 if it has 4 and so on. So all permutations and combinations, all such combinations, one attribute, two attribute, three attribute, everything else. That's why it's become exhaustive, and that's why we have said that it's not easy to compute. So it's exponential. Supposing if you have 100 attributes, now imagine, I think you have studied in ADA that permutation and combination is more exponential, factorial, it becomes factorial. All combinations you have to find out. Factorial is nothing but combinations, right? Mathematically. So that's exactly the problem. If at all, supposing if you have a relation where you don't have any fixed attribute only on left, fixed attributes only on right, and everything goes into both the sides, then the logic is very simple that you pick one attribute at a time, find its closure. If it not finding all attributes, right, go for two at a time, three at a time, all combinations here. So you have an algorithm already available for that. You can borrow it. Any doubts?
No, sir.
So